Hey guys, Ben here. I thought I'd make a quick video that shows how I normally design circuits with transistors. So today we'll focus on just switching things on and off, like actuators. Most of the time you have a microcontroller and want to control something like a motor or solenoid or something. So this video will show you how to size the transistor and set it up. So let's zoom in and I'll show you what I've got. Okay, so one of the most common tasks that I need to do with a transistor is just to turn something on or off. So not really amplifying a signal, it's just acting as a switch. So I drew a couple diagrams here. Today we're going to be controlling this, which is an air valve, a solenoid air valve. And it's a 12-volt device. You just put power on it and it opens. Pretty simple. So I just drew it in this diagram as a coil, which is a good way to represent it. It's like an iron core coil. So to turn the thing on and off, we could either put a switch between the coil and ground or between the coil and our voltage source. It doesn't really make any difference to the coil, but it will make a difference to us later if we choose a switching component. So I listed off a few of them, and I'll describe why I did or didn't pick them for this project. We could have used a relay. It's a bit overkill. In fact, this one is quite overkill. It's big and expensive, it's mechanical, it doesn't switch very fast. The best things about relays is that they can handle very high currents and they isolate the circuit. They isolate what is being switched from the control circuit. So we'll save that for another day. Similarly, a solid state relay, also a very cool component, mostly used for isolation and high voltages or high currents. So save that one. A MOSFET or an IGBT, also for much, much higher currents. They don't isolate. Well, I guess they sort of could, but we're not going to use these today either. A Darlington transistor. This is actually not a bad choice. Today we don't need to use a Darlington, but I think I'll probably do a video on these later because they actually are quite useful in some circuits, generally for higher current stuff. Today that solenoid doesn't really use that much current. So we're going to use this little guy, a standard bipolar transistor. Bipolar is just a plain transistor. That's what bipolar means. And this one happens to be a PN2222A. And this little tiny case here is called a TO92 case. So the first thing to do when picking a bipolar transistor is to decide whether we're going to use NPN or PNP. You may have heard these terms floating around. So I made a little diagram here to help us decide which one we're going to use. First off, the schematic symbols. The arrow in the symbol always is in the direction of the conventional current flow. And the arrow always points to the N material. So NPN or PNP. So that's one way to remember it. Also, watch out. I switched the emitter and collector on this between these two in the diagram here. So it's collector base emitter, emitter base collector. So in a PNP, the conventional current flow goes from the emitter to collector, and in an NPN, it goes from collector to emitter. So you may be wondering, well, you know, what can we do with all of this? Basically what we're going to do is put one of these in place of the switch here. And the two terminals of the switch are going to be the collector and emitter, or emitter and collector, depending where we put it in the circuit here. And the way that we get these switches to turn on or off is by either pouring current into the base, in the case of an NPN, or drawing current out of the base, in the case of a PNP. So it's a switch that is controlled by a current flow. Okay, so a minute ago I said that a transistor is a switch that is controlled by a current flow, and that we were trying to decide between PNP and NPN for our circuit. So how do we actually decide? In this case, the thing that's going to make the decision for us is our control signal. And in this case, it's going to be our favorite 0 to 5 volt logic signal. That this could come from a microcontroller or a PC parallel port or a number of different things. So let's look at each case. If we went for a PNP, transistor and we have this either 0 volt or 5 volt control signal, we don't have an easy way of controlling how much current is going to flow out of the base of the transistor to turn it on and off. And the reason for that is if the base is at 5 volts, or we have a 5 volt signal and then there's some sort of circuitry between it and the transistor, there's going to be a current flowing from our supply voltage. In this case it's like 12, but it could be a number of different things. And in the two cases of the base being 0 or 5, there isn't really an easy piece of circuitry we can put here that will allow us to control the base current flowing from the emitter to the base in the case of a PNP. However, in an NPN transistor, we have a really great option. It's just a resistor. So when this is at 5 volts, we have a current flowing from the base to the emitter, and that's going to turn the transistor on. And when this is 0, no current is going to flow, and the transistor will be off. So this is perfect. So in this case, the NPN is an obvious choice. In fact, in all of my projects, I probably use NPN transistors 95% of the time. In switching applications like this, I think you would almost always want to use an NPN. So just keep that in mind. I think in general, NPNs are quite a bit more common. So let's talk about actually choosing a transistor and setting it up with this solenoid valve. So we've decided to go the NPN route because it's easier for us to control the base currents with an NPN in the type of circuit that we're using here. And I said that a transistor is a current amplifier or a current controlled switch. So if we pour some current into the base and it flows from the base to the emitter, that will turn the transistor on and allow a large current to flow from the collector to the emitter. And the amount of amplification is known as the transistor's gain. So a transistor with a high amount of gain will allow a large collector current to flow with just a small base current, and a transistor with not much gain will not have as much amplification. And that amplification factor is known as HFE, or it's also sometimes called beta. That's the gain of the transistor at DC. I should also point out that we're not talking about AC circuitry here at all. This is all just steady state DC analysis to make our lives easy. What we're going to do here is pick a transistor, and this is a little bit where experience comes into play. I mean, there's thousands of transistors available. How do you pick one? Well, for hobby projects and sort of small scale design like this, there's really only a handful that come up. So I'm just going to say that we're going to pick the PN2222A, which is a really great low, medium power, very inexpensive, easy to use switching transistor. And it has a beta of about 100. We could be more conservative than that, but we'll just say beta is 100 for this particular transistor. It varies quite a lot. And I mentioned Darlington transistors earlier. Darlington transistors are basically two transistors ganged together to increase the gain. So those can have gains of like 10,000 or something. And that could be quite useful for switching higher current loads while keeping your base current low. So anyway, so let's get back to the design that we're actually doing today, this solenoid valve. This is a clippered solenoid valve, and if we get the spec sheet in here, there's not very much for electrical specifications. It just says 0.67 watts at 12 volts. They make this in 12 or 24 volts. This is a 12 volt variant. So we've got our schematic representation here, 0.67 watts at 12 volts. Well, we want to know the current, so we use Ohm's law, which is current times voltage equals power, or in this case we want to go in reverse. 0.67 watts over 12 volts. Put some units on there for you. I'll just type this one up. Is 0.0558 amps, or about 56 milliamps. Okay. So if we didn't know which transistor we were going to use, you could just start looking down the list of transistors in a catalog and think to yourself, well, the transistor is at least going to have to handle 56 milliamps, although you'll find that pretty much every single transistor can handle more than this. So this is not a very big requirement here. So what we know at this point is that we're going to use an NPN transistor. It has to handle 56 milliamps from the collector to the emitter. And now we need some way of turning the thing on and off. And if we did decide to use the PN2222A, we know that its beta is 100. So what we have here is our transistor, and IB, the base current, is flowing like this. This is grounded. This is the coil with our voltage source. And this is the collector current flowing through the coil to ground. And I said that beta is 100, meaning that this is 100 times less than the collector current. So IB is equal to 56 milliamps over 100, or 0.56 milliamps. So now the question is, how do we get 0.56 milliamps to flow into the base? Luckily, there's a really easy way. We can just add a resistor. So if we put a resistor here and then send this over to plus 5 volts, if we size the resistor correctly, we'll get exactly 0.56 milliamps to flow through here. The transistor will multiply it by 100, and we'll get the current to flow through the coil. So let me draw this a little bit more clearly, and then we can choose our resistor value. So our circuit is almost done. This is a pretty good, almost finished version of it here. We've got a resistor on the base where we're going to put our 0 to 5 volt signal, and the coil is connected here, the solenoid is connected here, so that when the input is 5 volts, we get a current flowing through this resistor, which turns the transistor on and allows a large current to flow through the coil to ground. So you're thinking, yeah, but I live in a voltage world. How do we actually get this thing to turn on and off? So we put this resistor here to convert our input voltage to a current. And you might be thinking, well, that's easy. I'll just use Ohm's law. 5 volts over the resistor value gives me the current. Almost. There's another little twist here. The base current is actually 5 minus 0.7 divided by the base resistor. And this 0.7 is an intrinsic value to silicon transistors. This is an NPN, so there's a PN junction here. And silicon PN junctions will drop a voltage. And for pretty much all transistors, I think it's about 0.7 volts. I think it's 0.6 volts for diodes. I'm not exactly sure why that is, but maybe you can look that up. And so we know that to get our coil working, we needed 56 milliamps to flow. So the IC has to be, let's say, equal to 56 milliamps. And I said that the transistor amplifies current by 100, so we need at least 0.56 milliamps to flow through the base. But it's actually a better design practice to shoot a little bit higher, because we want to make sure that the transistor is fully on. What would happen if we gave it less base current? Let's say we only gave it 0.1 milliamps in the base. So you'd multiply that by 100, and we get 10 milliamps flowing through here. And that would not be enough to activate our solenoid. So the way we have it designed now, if we chose a base resistor that only allowed 56 milliamps to flow through the collector, the circuit would just be on the cusp of working. So we want to design it to be a little bit safer. So let's just say we want to shoot for a base current of 1 milliamp. So we use the multiplication factor of 100, and we get 100 milliamps through here. So you might be thinking, well, wait a minute, how do we get 100 milliamps flowing through this? The answer is that we actually don't get a full 100 milliamps because the current is limited by the solenoid itself. If we were to short this, or if we were to connect the solenoid directly to 12 volts and ground, it's only going to flow as much current as the manufacturers rate it, 56 milliamps. So a transistor can't allow more current to flow through the device than it would normally use on its own, but it can restrict the current. Okay, so let's solve this guy. We've got IB is equal to 5 minus 0.7 over RB, and we know that IB is 1 milliamp. So when doing the calculations, always use the standard units. So enter this as 0.001 amps. $4,300 ohms. Well, they don't make 4,300 ohm resistors, so we could either use a 4.7K, and since we were pretty safe on our factor of choosing 1 milliamp for the base, this 4.7K resistor will flow a little bit less than 1 milliamp, but we'd still be pretty much okay. So there's one other thing I wanted to add here. For this particular circuit, since we're switching a coil, it's actually very important that we add a clamp diode. And that's going to look like this. So you might be thinking, well, that's stupid, but I mean, the diode is pointing into our voltage source. How could this ever get higher than plus 12? And the answer is that when the transistor turns off, all of that current that was flowing through this coil has created a magnetic field in here. And when the transistor turns off, that magnetic field collapses and the voltage is going to rise at this point. It could be quite significant. If the coil has a lot of inductance, the voltage could get to be, hundreds of volts here, high enough where it would actually blow out the transistor. So it's extremely good design practice to put a clamp diode in there. It could be a real problem because you might design this and switch it 20 times on the test bench and it works fine. And then you go out and put the circuit into service and it switches and it gets to be just high enough and it blows your transistor out. So definitely put a diode there. And you can also take it one step further and add a capacitor in there as well, like this. And this can be small, like 0.001 microfarads. And the capacitor will smooth out the pulse here and give the diode time to turn on and make sure that there's absolutely no spiking or voltage rising going on in here. So let's build it and test it and prove that the thing actually works. Okay, so here's the circuit. Yellow is plus 12 volts, black is a common ground, and red is plus 5. We've got our transistor here, the PN2222A, 4.7K base resistor, and our clamp diode. So if we put 5 volts into the resistor, control the valve quite nicely. So what we've done here is taken a very, very small signal, 5 volts at 1 milliamp or less, and are able to control, admittedly a pretty small signal, but we've taken care of the inductive kick from the solenoid valve. So I thought of just a couple of other things you might be wondering about. Throughout this, I was kind of trying to get the base resistor value chosen, and you might be thinking, well, screw it, we'll just put a 0 ohm resistor, we'll just short this thing out and make sure we have enough base current. But unfortunately you can't do that because the transistor will draw so much current through the base it will destroy itself. So you have to have a resistor here, or else the transistor will self-destruct the very first time you use it. In fact, when I was getting started in electronics, I thought a transistor was basically just a voltage controlled device. And so yeah, I put 5 volts on that base, and oddly enough, it didn't do anything. It didn't switch. It didn't allow current to flow. So I tried another one, same thing. And I thought, man, these transistors are just totally defective. But as it turns out, they were just being destroyed instantly. So you have to have a base resistor here. Also, there's going to be a voltage drop across here. So I said that there's a 0.7 voltage drop here. So if we measure all these voltages, we've got 5 volts here, we got 0 volts here, we've got 0.7 volts here. That's 5 minus 0.7 over RB across this resistor gives the current flow through here. But what's the voltage right here? This is actually pretty interesting. This voltage could be close to 0, or it could be about 0.1 or 0.2 volts, depending on the transistor and how much current is flowing through it. So I said that the reason we have a 0.7 volt drop from the base to the emitter is because that's the way silicon semiconductors are built. We've got a p-n junction here. Throughout the from the collector to emitter, there's a p-n and an NP junction, so that 0.7 volts cancels itself out. So if the transistor is perfectly built, the voltage here will be 0 when the transistor is fully conducting. So, but you know, the problems in manufacturing, and I think they might even build them asymmetrically on purpose or something. So actually, let's measure it and see what we've got. Turn our circuit on. Okay, sorry about that, guys. I had the wrong voltage set on the supply here, so we've actually got 0.117 volts. Sorry, and you can see this thing right about there. We've got 0.117 volts, which is what you would normally expect for a circuit designed like this. So keep that in mind. If your device requires exactly 12 volts across it, you're not going to get a full 12 volts with a transistor like this. You're going to lose 1/10 of a volt in the transistor. So I hope that about covers it. Obviously, transistors get quite a bit more complicated when talking about switching things at AC. When you start talking about frequency gain and stuff, it adds a whole other level of complexity. But I hope this gets you started with DC design. So let me know what you think. Let me know if you have any questions, and I will see you next time.